I'm challenging you to make it through this video. This integral is no joke, and we're going to have to draw upon a couple of pretty powerful functions to get the job done. But if you can make it through, I promise it will be worth the wait and the struggle because the answer is pretty remarkable. The first tool we'll need is the Lambert function, usually denoted with a W. Here's its series representation. Why do we care about this? Well, the Lambert function is the inverse function to x times e to the x. And remember how inverse functions work? When we compose them either way around, they essentially undo each other and they just spit out x. So when we compose w and x times e to the x either way around, we just get out x because they're inverse functions. The next tool we need is the gamma function. It probably deserves its own video, but the gamma function is the generalized factorial function typically defined as this improper integral. The last major tool we need to solve this problem is the Riemann zeta function and its cousin, and I'm not going to be able to say this correctly, direct eta function. Since the eta and the zeta functions are so similar, they have a very nice relationship that lets us transfer between the two. Now that we have all the tools we need, let's get after this problem. Now, I certainly don't know how to integrate this as is. Let's find a different representation for our integrand and integrate that. I'll just call our integrand y, and the first thing to notice about it is that it's this ascending tower of x to the x. It's like this infinite iteration, and another way to write this would be y equals x to the x all to the y. It has this repetition pattern to it. We could keep substituting x to the x to the y in for y, and it would build this infinite tower. Writing it like this lets us take advantage of our properties of logarithms. Let's take the natural logarithm of both sides here. So ln of y equals ln of x to the x to the y. With properties of logarithms, we'll take this y down front, and this will be y natural log of x to the x. And now, for seemingly no apparent reason, we'll insert an e to the ln. Remember that e and ln, the exponential function and the natural logarithmic function, are inverses of each other. They undo each other, so we can insert them. I'm just going to put an e to the ln right here around this y, and this is completely legal. Now let's take this and divide both sides by this e to the natural log y term. And maybe you can see where we're going if you think back to that Lambert function. Remember that the Lambert function is the inverse function of x e to the x. So this is pretty close, isn't it? We have a natural log y e to the natural log y. So let's make these exactly match up by taking the negative of both sides here. Compose both sides with w, and we can finally take advantage of the property that w of x e to the x is simply x. Or really, x in this case is minus natural log y. So now we've composed those, we've canceled things out with the Lambert function. We're only a few steps away from solving for y. So ln of y is minus w of minus ln of x to the x. Or we could take the e of both sides and say that our original y is also equal to e to the minus w of minus natural log of x to the x. Now, thanks to those inverse properties of the Lambert function, we can rearrange this so we have e to the minus w of something in the exponent. Let's do just that. Let's divide both sides by x and divide both sides by e to the w of x. W of x over x equals e to the minus w of x. And now we have yet another representation for what we have as y. Just match these things up, and we now have y as, well, it's w of x over x, but it's not x in this case, it's minus ln of x to the x. So this will be w of minus ln of x to the x all over x, which in this case is minus ln of x to the x. And maybe let's just take advantage of those logarithms one more time to drop down these x to the x powers. And we're finally getting somewhere. This is something we can integrate. So now our job is to integrate this. How do we do that? Well, remember that power series representation of w? Let's plug minus x ln x into that series representation. Glossing over a few of the algebraic details, this is our new integrand. So let's switch these symbols everything that doesn't have an x attached will pull out of the sum. So we've separated these, and maybe this is a little bit of a cop-out, but this integral right here is a variant on the gamma function. This is something I would probably look up on a table of integrals. So let's just replace this. And we've performed all the integration we need. We just need to figure out what this sum equals and we'll be all set. How many negative ones do we have? We have 2 to the n, we've got a minus 1 to another n, that's 3 n's, and an extra negative would make an extra 1. So this negative 1 is to the power of 3n plus 1. This 1 over n to the n would cancel with this n to the n, and we'd have an extra 1 over n left over. Gamma of n is equal to n minus 1 factorial, and so the n minus 1 factorial over the n factorial is another 1 over n. If we start writing out the terms of this series, what we're seeing is that this is the eta function evaluated at 2, and we have that relationship between the eta function and the Riemann zeta function. And if you compute this, this is a half. So we have 1/2 of the Riemann zeta function at 2. And so we're finally here. Our original problem, which we rewrote using the Lambert function, integrated using the gamma function, defined it as the eta function, which is 1/2 of the zeta function, 1 over n squared. This is the zeta function at 2. This is a famous, well-known result. 1 over n squared from 1 to infinity. This is pi squared over 6. And so our final answer is pi squared over 12. What an amazing result. So much went into this. It's hard to believe that this is the crazy answer that we got. If you're looking for the decimal representation, this is about 0.822. This shape is known as a bell curve, or we might call it a Gauss curve. It's super important for many reasons. One of the most popular applications is the normal probability distribution. This symmetrical shape describes a lot of phenomenon in the real world. And the way we use it to find probabilities is by measuring the area under a curve between different values. We have to account for some normalizing constants, but really this shape comes from this function e to the minus x squared. And you know, if we want the area under this curve, well, we're going to have to do some integration. And this function, I don't know how well I've drawn it, but it stretches forever to the left and to the right. It has an infinite domain, so we want to integrate this thing over its entire domain to find the area. So this is now our problem, the definite integral from minus infinity to infinity of this function, e to the minus x squared dx. And what you may notice is that none of the regular integration techniques work very well here. There's no like u substitution or integration by parts that's going to be able to solve this. And we could use a power series, but that's going to get a little bit clunky. That's maybe how we would do it if it wasn't a definite integral, if we didn't have any bounds. So here's the trick, here's the technique. We're going to just call this I for integral, and I'm going to square both sides of this equation. I'm going to square this entire integral. Not something you're used to doing, but what does something squared really mean? Well, it means times itself, so this just means the definite integral from minus infinity to infinity of this times itself. Now, a subtle trick here that this quantity, it didn't really matter that I called it x, right? We could have used t's or z's or y's, and I'm going to use a y here to represent the other one. And it's completely equivalent because when we actually integrate this, well, all the x's go away, don't they? Think fundamental theorem of calculus. We end up just plugging in for x. So it doesn't matter what letter we use here. I'll just call y on this second integral, and these are being multiplied. But it's the same quantity, they're both I, so this is I squared. And actually, since both the letters are completely different here, and they have the same definite bounds here, minus infinity to infinity, this is what's known as separable. These integrals are separable. If you go into multivariable calculus, you might try to split up these integrals to make them easier. Here we're going to combine them. So this is exactly the same thing as a single definite integral, putting these both inside the integrand. So They're both base e. When we multiply like bases, we add the exponents. So minus x squared minus y squared, that's the same as minus x squared plus y squared in the exponent. And then we have, I really should need two integrals here. We're integrating twice. We're putting these together. And I'll just say dy dx. If you've had some experience in multivariable calculus, you might know where we're going next. This is still a pretty wonky integral to solve, but it's in rectangular coordinates that's making it wonky, a square coordinate system. But x squared plus y squared, think Pythagorean theorem, think trig, think the fundamental trigonometric identity. X squared plus y squared is r squared. The Pythagorean theorem, we're going to make a change of coordinates here. We're going to switch to polar coordinates. Instead of using rectangular, we will use the trig functions and the Pythagorean theorem to change this coordinate system. And I guess you could call it a substitution. I mean, really what we're doing is saying x squared plus y squared equals r squared. We're going to have to change these bounds. And in the polar coordinate system, dy dx, or dx dy, this turns into what's known as its Jacobian r dr d theta. So we're changing from x and y's to r's and thetas. And what we also need to do is change these bounds. So if you think about the polar coordinate system, we're instead thinking of not rectangles but circles. The radius r starts at the origin and extends forever. Well, originally, the x boundaries, when we think dx, were minus infinity to infinity, forever to the left and forever to the right. Well, for r boundaries, the r always starts at the origin, namely at 0, and then, in this case, continues out forever. So these bounds, the r bounds, will be 0 to infinity. And the y bounds, which were minus infinity to infinity for the same reason, turn into theta boundaries. Well, if you think about the unit circle, or just any circle, we get coterminal angles, so we can describe every single angle in one sweep of a circle, 0 to 360 degrees, or we typically use 0 to 2 pi radians. This is the substitution. And so at this point you might think, oh, we're good to go. Well, we actually have to make one more substitution. If I just gave you this integral in a Calc 1 or 2 class, you could probably figure it out via a u substitution. Letting u equal the minus r squared, that would make du minus 2r dr, and that's going to take care of this exponent and this extra factor of r, because our dr is going to be a du over minus 2r. So if you go ahead and make this substitution, this outer integral won't change, still 0 to 2 pi, but this integral, which was r boundaries, we need to change them to u boundaries. I like to make a little t-table here for u's and r's. Originally, r was infinity and 0. Well, if we plug these into our substitution, if r is 0, u will be 0, so this lower boundary stays the same. And if we plug in infinity, well, you can't really plug in infinity, but if we could, think order of operations, infinity squared would be infinity, and then negative, this would be negative infinity. And we should line these up just as they are. And maybe this feels a little bit uncomfortable. Typically, we like the lower limit of integration to be less than the upper limit of integration. We'll fix that with this negative that comes out of the substitution here, because our dr, that's becoming a du over minus 2r. We still have a d theta, we still have that r, and e to the minus r squared became e to the u. Well, thankfully now we're getting these r's canceling out, and we can even take this negative, and one property of definite integrals, if you multiply by a negative, it has the effect of changing the bounds, or flipping them. So really we could rewrite this definite integral 0 to 2 pi minus infinity to 0 e to the u du d theta over 2. And we're finally ready to actually compute this thing. If you don't mind, I factor out the 1/2, and we could even unseparate this now, kind of doing the reverse of what we did before. There are no thetas inside this integrand, so maybe you would want to just make this 0 to 2 pi of 1 d theta integral minus infinity to 0 e to the u du, and compute these separately. Looks like we've got 1/2. The antiderivative of 1 d theta is simply theta, and we're evaluating from 0 to 2 pi. And then this is being multiplied by the antiderivative of e to the u is e to the u, evaluated from minus infinity to 0. Now I'm being a little bit generous with my notation here. We can't really evaluate at negative infinity, but what we can do is take the limit. So traditionally what we would do is let t approach negative infinity here. I don't have enough space on the board, but just know that that's really what we're doing. We're really taking the limit here when I plug in minus infinity. So it looks like we're getting 1/2. If I plug in 2 pi, that'll be 2 pi minus plug in 0, that'll be 0. And this is being multiplied by e to the 0, which is 1, minus, and again, I'm not really plugging in infinity, but if I could, it would be e to the minus infinity, which tends towards 0. Think of the graph of e to the x as that horizontal asymptote along the x-axis. As we go all the way to the left, e disappears. So really, this is like 1/2 times 2 pi times 1, or simply pi. Wow, did you expect a pi to fall out of here? And we're not quite done yet, because if this equals pi, this was the square of what we actually wanted. So really, if we take the square root of both sides, well, we'll get what we want. We'll get our original integral. Quite amazing that the area under that curve is square root of pi. And this is where, if you've ever seen these normal curves and the formulas for them, you'll see a square root of pi or a square root of 2 pi when we kind of adjust for some things. A pretty amazing result from a pretty amazing integral.
Everyone always wants to know, when are we going to need math? Well, how about for some free Wi-Fi, because this math meme promises you that if you can just solve this integral. Problem is, this seems like a tough one. But truth be told, you don't actually need any calculus to solve this. You just need to know what a definite integral represents geometrically and a little bit of algebra. So what does this definite integral really represent? Well, definite integrals give us the area under the curve of this function. So we're just interested in the area under this function from -2 to 2. And really, we can think of this as two separate functions if we do this distribution. So what's the area under the curve from -2 to 2 for these two functions? Typically, we'd have to do a bunch of calculus nonsense, but the fact that we're integrating over a symmetric interval, -2 to 2, gives us some very important clues. You see, if we do this for an odd function, on one half of the interval, the area will be negative. On the other half of the interval, the area will be positive, and it will cancel everything out. And so it doesn't really matter what the function is. If we're integrating an odd function over a symmetric interval, the area will end up being 0. And although this function is quite wonky, we can just rely on the algebraic fact that x cubed is an odd function, cosine of x over 2 is an even function, and the square root of 4 minus x squared is also an even function. When it comes to these functions, an odd times an even is an odd. And so this function that we're integrating over a symmetric interval is an odd function, meaning the entire integral is 0 for this part. All we have to figure out is the part of the integral that's just 1/2 square root of 4 minus x squared. Now this isn't an odd function, so we can't use the same trick, and you might think we have to actually do some calculus here, but no. Integrals are just area under the curve. And this function happens to be a semicircle of radius 2. So all we need to do is compute the area of this semicircle, multiply it by 1/2. Hey, wouldn't you know it, we're getting pi. which is like super frustrating because the Wi-Fi password is the first 10 digits, and you'd probably have to use the internet to look up those digits in the first place.
Take a look at this wild integral. If you were in Calc 2, you would probably start off with a trig substitution. Let's give it a try. See that x squared plus 1 in the denominator? That looks an awful lot like the trig identity tangent squared plus 1 is secant squared. So if we let x equal tangent theta and substitute that into the denominator, we'll get that identity. We'll have to substitute tan theta in for x in the numerator, and since we're changing the variable, we're going to need to change the differential. Let's take the derivative to get dx. That'll be the derivative of tangent theta, which is secant squared theta d theta. Lastly, let's just change those x bounds to u bounds. If we plug in 0 for x, we'll see that's also 0 for theta. If we plug in 1 for x, that will be pi over 4 for theta. So we've transformed our integral, but we're not quite at a place where we can integrate this yet. Sometimes it's easier to rewrite trig functions in terms of sine and cosine. Let's do that. Tangent is sine over cosine, and let's go ahead and combine with the plus 1, get a common denominator. We'll have sine plus cosine over cosine inside that logarithm. When you have the log of a quotient, it's just screaming to use properties of logarithms, so let's do the log of the numerator minus the log of the denominator. Things seem to be cleaning up quite nicely, but we're still no closer to actually integrating this. We know sine squared plus cosine squared is 1, but what about sine to the first plus cosine to the first? Inside the logarithm, no less. This is where things get a little bit tricky. Notice that we're already subtracting a log of cosine. Maybe we could rewrite sine plus cosine in terms of just cosine. Essentially, we're going to derive a less well-known trig identity. Let's just say sine plus cosine equals some constant times cosine of theta plus some other constant. Luckily, we do have the very well-known trig identities for cosine of a sum or a difference. Let's just apply that here. We have sine thetas on the left, we have sine thetas on the right, we have cosine thetas on the left, we have cosine thetas on the right. Let's do matching coefficients. The coefficients on the left side are 1. The coefficients on the right side, well, they're a little more complicated, but they have to equal 1. Now we can take advantage of the fundamental trig identity, square both sides of both these equations, and add them up. Then we can factor out the constant. Sine squared plus cosine squared, that's 1. 1 plus 1 is 2. This lets us solve for one of our constants as square root of 2. Substitute this value back into those two equations and take the inverse trig functions. It'll let us solve for that other constant we were looking for. And so whether you realized it or not, sine theta plus cosine theta can be written as square root of 2 cosine theta minus pi over 4. So now, once again, we have the log of a product. Let's just split that up into separate logarithms, and we'll use properties of logarithms to drop that exponent down front. Time for the fun part. Maybe you don't think we've actually done anything to help us integrate this. Well, we can integrate that first part. It's just a constant, so that's not really a big deal. But look at those two cosines inside the logarithm. They're pretty similar. One's just theta, the other is theta minus pi over 4. And we're integrating from 0 to pi over 4. Cosine is an even function, so theta minus pi over 4 is the same as pi over 4 minus theta when it's inside cosine. Do a u substitution here. Let u equal pi over 4 minus theta. That means du equals minus d theta, and this integral can be rewritten as negative natural log cosine of u du. To change the bounds, when theta is pi over 4, u will be 0, and when theta is 0, u will be pi over 4. So look at these two definite integrals. They're the same thing. Their underlying variables are different, but if we were to compute the integrals, the values would be exactly the same. We have an addition of one, a subtraction of the other, and so they cancel each other out. All that's left to do is anti-derive this constant by multiplying it by theta, substitute in pi over 4, and there you go is our answer to that slick definite integral. Golden integral, which admittedly is a little intimidating. now that you know what phi is and having it show up in those exponents. To solve this, we'll have to know a few facts about the golden ratio, namely that it's a solution to this quadratic equation, which is to say phi squared minus phi equals 1. Or dividing by phi gives us 1 over phi equals phi minus 1. Keeping that in mind, how should we tackle this integral? One way is via a very slick substitution. Let's let u equal x to the phi. That makes du phi times x to the phi minus 1 dx using the power rule. Or du over phi x to the phi minus 1 is dx. Notice that we don't have to change our limits of integration, since when x is 0, u is also 0, and when x tends towards infinity, so does u. Making this substitution leaves us with a bit of a cluttered integrand though. The 1 over phi is a constant, we can pull that outside the integral, but the only variable inside should be u, now that we're integrating with respect to u. To see what's going on, let's break that x up using properties of exponents. And looking back at our substitution, we know what x to the phi is. It's u. But what is just x? We can solve for x in terms of u by taking our substitution equation to the 1 over phi power. Now u to the 1 over phi is x, and we can complete our substitution. What we have now should remind you about those facts of the golden ratio, namely 1 over phi equals phi minus 1. Let's replace that and combine these u's once again using properties of exponents. Now, I've left these exponents this way for a very specific reason. And using just a little bit of trickery, I'll rewrite the exponent in the denominator as well. Why do this? Well, frequent viewers of this channel might know I'm a pretty big fan of the gamma function, but not in this video. Gamma doesn't show up here, it's gamma's cousin, the beta function. In fact, what we have here is a variant on the beta function. We just have to be very careful with how we match things up. X in the beta function is phi minus 1 inside our integral, and y in the beta function is just 1 inside our integral. That's why we left the exponents the way that we did. Noticing that actually completes our integration. We have 1 over phi, beta of phi minus 1 and 1. The beta function actually does evaluate to a combination of gamma functions, so what we have is 1 over phi times gamma of phi minus 1, gamma of 1 divided by gamma of phi minus 1 plus 1, gamma of phi. The gamma function is the generalized factorial function. Gamma x is x minus 1 factorial. Thus we have phi minus 2 factorial, 0 factorial, which is 1, and phi minus 1 factorial. We can simplify this using properties of factorials. Phi minus 2 factorial over phi minus 1 factorial cancels to 1 over phi minus 1. This solution is pretty elegant because, one more time, remember 1 over phi is phi minus 1. These cancel out and we get 1. That is an absolutely incredible result.
We'll start this off in a similar way we often do with these types of problems, properties of logarithms. Insert an e to the ln so that we can drop that exponent down in front of the logarithm. This is a very common technique. And part of the reason we do it is to take advantage of the Taylor series, the power series for e to the x. It's not just x that we have here, it's x times natural log x, but it fits into the formula all the same. To keep going, we do have to switch the integral and the summation sign, which you can't always do, even though quite often you can. I made a video you can check out in the right-hand corner addressing this issue. Now that we've switched these, let's pull out everything that only has an n attached. That way all of the x's are inside of our integral. This is probably also a good place for me to point out that you might have to worry about some domain issues when you're doing things like this. That 0 as the lower limit might give you some heebie-jeebies. We'll just let it go. And here comes really the challenge of this integral. How on earth are we going to do this? Spoiler alert, I'm not going to use the gamma function. I'm going to do a technique from another video that I've done, the Feynman trick, or differentiating under the integral. You can check out a full video on that topic here in the right-hand corner, but we did a really similar technique, starting with just x to the n. Notice we can integrate this without much issue, just regular old add 1 to the power, divide by the new power, and evaluate using the fundamental theorem of calculus. What gets really interesting about this is when we differentiate both sides, specifically partial differentiating with respect to n. Glossing over some of the details, what this trick allows us to do is slip the differentiation operator inside the integral and differentiate under the integral sign. Now be careful here, the variable of differentiation is n, so remember your rules for differentiating when the variable is the exponent. The derivative of x to the n with respect to n is x to the n, natural log x. And we can differentiate the right-hand side in the normal way, either with the quotient or reciprocal rule. And you might say, so what? We only have a single power of natural log. We have n of them in our original problem. Well, let's just differentiate this n times. It's a little harder to see if you actually differentiate n times and multiply everything together. So this is what it would look like after differentiating 100 times, or if you differentiate k times, you can really see the distinction between the powers of x and the powers of the natural logarithm. And at this point, I would just let k equal n to get this. And in my opinion, that's a pretty cool expression just for that integral alone, but that was not our original problem. Our original problem was this sum with this integral inside. So now that we have this, let's put it all together. And nice things happen. Effectively, the n factorials cancel out. We get this really adorable sum. You can start writing it out. And if you put this into a computer without using too many terms, you'll get a really nice approximation. You, of course, can verify that this does converge by one of the tests from Calc 2.
Start by making the substitution u equals square root tan x. This would mean the same thing as u squared equals tangent x. That'll make it a little bit nicer for us to find du when we take the derivative of both sides. 2u to the first du will be the derivative of tan x, which is secant squared x dx. Or if you prefer to solve for dx, 2u du over secant squared x is dx. Making these substitutions inside of our integral is going to leave us with this secant squared x in the denominator, and since we're integrating in terms of u, everything in our integrand should be u's. What is secant squared x in terms of u? Well, head back to our substitution. If we square both sides of our substitution, that would mean u to the fourth is tan squared x, and via that nice trigonometric identity, tangent squared x is the same as secant squared x minus 1. That's pretty convenient because now we can solve for secant squared x by adding 1 to both sides. Secant squared in this case will be u to the fourth plus 1, and we can substitute this into our integral. Now we have a new, but admittedly still challenging integral to solve. Here's the very fancy algebraic footwork. Divide every term, the top and the bottom, by u squared. So, in a sense, we're multiplying by 1 over u squared over 1 over u squared. Our integral will reduce to 2 over u squared plus 1 over u squared. Why do this? Well, the denominator, very subtly, can be written in two ways using a perfect square. If we look at the denominator and add 0, a very special 0, 2u over u minus 2u over u, that's an addition by 0. And if we write the terms this way and factor, we get this expression, or we could do it this way and get this expression. What we have is two different representations of the denominator. Why do we need two? Well, let's add another 0 in the numerator. This time we'll add and subtract 1 over u squared, and we'll also break up the 2 as 1 plus 1. All of this fancy algebraic footwork is so we can split up this integral into two different integrals. The first with the numerator 1 minus 1 over u squared, and the second with the numerator 1 plus 1 over u squared. The denominators are the same, but for the first integral, we'll use the representation for the denominator, which is u plus 1 over u all squared minus 2. And for the second denominator's representation, we'll use u minus 1 over u all squared plus 2. That was a ton of jumping through hoops just to get these representations of our integrand. Why do all of this nonsense? Well, it gives us a chance to again use very straightforward substitutions. Let's let z equal u plus 1 over u, and let's let y equal u minus 1 over u. That makes dz 1 minus 1 over u squared du, and dy 1 plus 1 over u squared du. These substitutions clean up our denominators very nicely, and hey, wouldn't you know it, it completely clears the numerator when we substitute in our differentials. How do we compute these antiderivatives? Well, these are actually direct formulas to get the inverse tangent functions. So we end up with minus 1 over root 2 arctan of z over root 2 plus 1 over root 2 arctan of y over root 2 plus some constant c, of course. But we knew what z was. Z was u plus 1 over u. And we also knew what y was. Y was u minus 1 over u. But we actually started with x's. So what was u? U was the square root of tan x. And we have this final, very long, very wonky solution, which if you were to take the derivative with respect to x, we would get square root tan x.
Can you compute this using standard integration techniques? I'll be honest, if you can, I'll be very, very impressed. What you learn in calculus probably won't do the job for this, but we could compute this integral if we just take away the natural logarithm. This is just the opposite of the power rule. Add 1 to the power, divide by the new power, and we can just evaluate using the fundamental theorem of calculus. And if we wanted to be a little bit more general, well, we could just do this with the variable n instead of having an exponent of 100. It works out the exact same way, and we get the answer in the exact same way too. Notice that this is an equality. So if I differentiate one side, it's the same as differentiating the other. And I'm going to take the derivative, the partial derivative, with respect to n. And this is the trick I'm really trying to show you here. The fact that we can take this partial derivative inside the integral. This is known as differentiating under the integral. It's often called the Feynman trick or the Leibniz rule for integrals. Taking the derivative with respect to n, we have to remember our rules for differentiating exponential functions. This derivative is x to the n natural log x. This isn't the power rule. We're differentiating with respect to n here. So this is an exponential function with base x. And interestingly enough, we've solved a similar type of problem we had before. It's just we only have the natural log x to the first instead of to the 100th. But what if we kept going? What if we took the derivative of both sides again? Well, on the left, we would just move the derivative inside the integral. We'd take the derivative of x to the n again, which would be x to the n times ln x, and we'd have ln x squared. You could multiply these numbers together in the numerator on the right-hand side, but I think I'll leave them like this so that we can see the pattern. Keep taking derivatives like this. Our third derivative, we'd have x to the n ln x cubed on the left-hand side, and on the right, minus 1 cubed times 3 factorial over n plus 1 to the 4th. See if you can notice the pattern. If we took 100 derivatives, we would get on the left-hand side something very close to the original integral we were trying to solve. And the pattern on the right, minus 1 to the 100th times 100 factorial over n plus 1 to the power of 101. And now we have a function that gives us this integral for whatever power of x we'd like. In particular, we wanted x's power to be 100. So let's just substitute 100. We'll have the integral we're interested in, and we get the result as well. Let's do another example so you can really see more about how this trick works. Here's a fairly challenging integral. I don't know how you would do this without using this trick. What we'd like to do is differentiate under the integral sign in a way that it makes our problem easier. To do that, we're going to have to define a new function so that when we take the derivative, it's a different variable than t. Let's define things this way. Why do it this way? Well, again, for the same reason, when we take the derivative of t to the x, it's t to the x natural log t. The derivative of 1 is 0, but the point is that the natural logarithm functions cancel out. And this is really the point of the trick. You want to take derivatives to either create the situation you want or create an easier situation for yourself. Now we have the derivative of our defined function as the definite integral from 0 to 1, but we're integrating with respect to t. Again, we can do this just using the fundamental theorem of calculus, applying the reverse power rule, add 1 to the power, divide by the new power, and substitute these variables. The difference here is that our result is actually the derivative of the function we really want. So really, we have to integrate this. If we take the antiderivative of 1 over x plus 1, it's natural log absolute value of x plus 1, and we need a constant plus c. This works out pretty nicely because if we substitute 0, natural log of 1 is 0, and so c is 0 as well. Our function is just natural log absolute value of x plus 1. Now we can substitute anything we want. If we wanted to compute our original question, which had a t to the 10th, just substitute 10. It'll be natural log of 11. Or just as easily, you could solve this integral with a t to the 100th by plugging in 100, and it would be natural log of 101.
This integral is called the Sophomore's dream. It's called that because the solution is pretty amazing. It's almost dreamlike that we get the answer that we do. Now just looking at it, x to the x power or x to the minus x power, you know there's going to be a bit of trickery involved here. Think about just differentiating x to the x. We have to do logarithmic differentiation, an entire technique just to do it. So you know that anti-deriving this thing is going to come with a bit of work. And we're going to start with the usual thing that we would do in situations like this, when we have a variable to a variable power, we often insert an e to the ln. Those inverse functions that cancel out, we can just insert them and take advantage of properties of logarithms. So let's do just that. Let's put an e to the ln in here so that we can use that property of logarithm. We can take that exponent and drop it down front. Let's rewrite this, same bounds, e to the minus x ln x dx. So how do we integrate this? And this is the first place we need to draw upon some outside knowledge. We're going to use power series here. Remember, the power series of e to the x can be given as this, the sum from 0 to infinity of x to the n over n factorial. This is known to be e to the x. It's just, we don't have e to the x, we have e to the minus x ln of x. So we'll use this sum, but we'll replace x with minus x ln x. So now what we have, integral 0 to 1 still, and we have this sum from n equals 0 to infinity. This is over n factorial, but instead of x, we have this entire exponent, minus x ln x. This is all to the n, and we still have dx. Now I'm going to take just a second to rewrite this integral, and I'm going to write minus ln x. I'm going to take this to the n, and then we also have an x to the n. This is over n factorial dx. And what we can actually do is we can interchange the summation and the integral symbol. We'll put the integral inside of the sum. And you might ask, well, why can we do this? And the reason is the uniform convergence of this sum. And that's all I'm going to say about that. And at this point, we need to rely on some substitutions. Here's the substitution we'll use. Let's let u be minus ln x. And notice that we would take care of this term, the minus ln x, that would become u, but we still have an x to the n left over. Let's figure out what x is, take the negative of both sides here, so that minus u equals ln x, or taking the e of both sides, we would have that e to the minus u, that's x. Also, of course, when we're doing this change of variables, we need our differentials to change. We need to find what dx will be. This means that dx, the derivative of e to the u is e to the u. Well, it has a negative here, so I need to multiply by a negative du. So we figured out our substitution and our dx. Let's rewrite this integrand. So what we have now, minus ln of x, that becomes u. X to the n, well, that will be e to the minus u to the n. So this will be e to the minus nu using properties of exponents. Still over n factorial. We also have dx. Dx we know to be minus e to the minus u. This is du. Now, since we've done a u substitution, we need to change those bounds. Those x bounds were originally 0 to 1. We need to change them to u bounds. So when x was 1, according to our substitution here, that would be minus ln of 1, which is 0. So this bound should change to 0. And when x is 0, that would be like minus ln of 0. Well, we can't really take the ln of 0. We know ln of 0 is undefined, but it does spike down towards negative infinity there. So it's kind of like negative infinity. We'll just say infinity here. Now these boundaries aren't quite very proper, are they? Infinity to 0. But there's a nice little fix here. If we just negate the integral, that has the effect of flipping the bounds. So I'll just use this negative symbol right here. In fact, let's just make this a positive and flip these boundaries. How about that? Let's just make this instead from 0 to infinity, and we'll make this positive. That'll be much nicer to deal with. Now, since we have some like bases going on here, e to the minus nu, e to the minus u, let's combine those, get a common base e to the minus nu minus another u. We could rewrite this, factoring out the u, as e to the minus n plus 1 times u. Looks a lot nicer, I think. So we're getting somewhere. There is this slight nuance of the n plus 1. I think let's make another quick substitution. Let's just let v be n plus 1 u, so that dv equals n plus 1 du. The bounds of integration won't change, but what we have now is that u to the n, well, that should change into v over n plus 1 to the n. I'll simply write that as v to the n over n plus 1 all to the n. The e to the minus n plus 1 times u, that'll exactly be e to the minus v, and du, well, that becomes dv over n plus 1. We're getting very close. Still need, there's an n factorial underneath here, and actually all of these n's here, n plus 1 to the n factorial, and n plus 1, none of those have a v in them. So they're all constants. We can factor them out of the integral. Let's just pull that out. We have this sum here, 0 to infinity still, and on the outside what we have is 1 over n factorial, and then I'll just combine these n plus 1's. We'll have an n plus 1, it was already to the power n, bump it up by 1, this will be to the n plus 1, times this integral from 0 to infinity of v to the n e to the minus v dv. And so finally, another piece of magic. What is this integral? Astute mathematicians might recognize this as the gamma function, the generalized factorial function. This actually is gamma of n plus 1, which is equal to n factorial. So we'll just slip that piece of knowledge in here, that entire integral becomes n factorial, and so what a great thing going on here, that this n factorial cancels with this n factorial. We just get the sum from 0 to infinity of 1 over n plus 1 to the n plus 1, and the magic that happens here is when we re-index this. Let's just change the index from starting at 0 to starting at 1. As I say, if we bump the index by 1, we'll bump everything else down by 1. This would change to 1 over n to the n. The n plus 1's just turn into n's, and you could even rewrite this using properties of exponents as n to the minus n. And wow, look at that result. It's basically the same thing. The continuous sum turns into the discrete sum. One's x to the minus x, one's n to the minus n. A pretty dreamlike result, if you ask me. We're going to solve this infinitely nested integral, the definite integral from 0 to 1 of square root of x plus square root of x plus square root of x, and it keeps going on nested inside this. This is a pretty gnarly thing to work with, and it certainly doesn't really follow any of the natural integration techniques you would learn in calculus. So let's figure out a different way to write this function. I'm going to call this function f of x, and it looks like f of x is the square root of x plus, the square root of x plus the square root of x keeps getting nested inside indefinitely. And so the thing we typically do sometimes with these nested or infinite tower things is we write it like this. We write it like kind of a recursive thing, x plus f of x inside. So this is how we should think about this function, and actually we can solve for what this function is just doing a typical quadratic equation thing. You could square both sides, so f squared of x, this would be x plus f of x. And then the typical way we solve a quadratic equation is we move everything to one side, so just make this f squared minus f of x minus x equals 0. And hey, we can even just use the good old quadratic formula on this. Usually the quadratic formula says x equals, but in this case it's not x equals, it's f of x equals. And then it goes like minus b, so b in this case is minus 1, minus minus 1 would be 1, plus or minus the square root of b squared, so 1 squared is 1, minus 4 times a, which in this case is 1, times c. Well, c is negative x. Typically we think of c as the constant term, but here c is actually the variable minus x. So minus x, I'll just say minus a minus is a plus, all over 2a, which is 1. So actually we have our function here, or we could say functions because it's a plus and a minus. Well, which one should we choose? Should we choose the plus? Should we choose the minus? Should we choose both? If you look at the integrand here, since our bounds are just between 0 and 1, and we know that if we plug in any value from 0 to 1 into the square root function, square root of x, it's going to be positive, or at least 0. And we could pretty much assume that if we were to keep nesting these square roots, we'd still get positive things under the square root. And in fact, the output here for this whole square root mess, it's going to be positive. So I don't think we should include the negative sign here. Let's just assume that this is plus. And now we have our function. And this we can actually solve via a good old U substitution. This could be a problem given to you in a Calc 1 class now. You could take out that 1/2, that would be fine. And we'll just take U to be the inside of the square root, 1 plus 4x. That makes du 4dx. And if you like, you could even say that dx is du over 4 when we make our substitution. So I think this will be 1 plus root u, or I'll just write it as u to the 1/2 power. That's typically how we think of this when we do antiderivatives. The dx becomes a du over 4. I'll write it like this. And maybe I'll go ahead and just change the limits of integration. These were x limits. We should change them to u limits. So I like to make a little table over here where x's and u's, we had 0 and 1. And if we plug 1 into our substitution, that would be 1 plus 4 when we let x be 1. So u should be 5. When we plug in 0 here, 1 plus 0 is 1. So our new limits of integration, I think, are 1 to 5. We're ready to take the antiderivative, apply the good old fundamental theorem of calculus. I think I'll just simplify 1/2 times a quarter, make that 1/8. The antiderivative of 1 du, that will be u. The antiderivative of u to the 1/2 should be u to the 3/2. Divide by 3/2, we divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3. And then we evaluate from 1 to 5 using that fundamental theorem of calculus. So I think if we go ahead, we can just plug these in. 1/8. 5 is for u, plus 2 times 5 to the 3/2 over 3. And then this is all minus, plugging in 1 plus, well, 1 to any power is still 1, so plus 2/3 here. I need a big parentheses for 1/8. Now you're welcome to crunch this number if you want. I'm a little bit out of space. I'll just write what this is, 5/12 times 1 plus root 5. This definite integral is pretty intimidating. Not only is it an improper integral, but we're integrating the product of two infinite sums. Let's see if we can start making better sense of these infinite sums by putting them in summation notation. By convention, let's have these sums starting at n equals 0, and looking at that first sum, clearly it's alternating. It goes from positive to negative and so on, so we'll need a -1 to the n. We see each term has an odd power of x. The way we can write an odd number here is 2n plus 1, where n is a natural number, so we'll have an x to the 2n plus 1. The pattern in the denominator of this first sum is what's tricky. Basically, that pattern goes like 2, 4, 6, 8, all the way up to 2n, the product of this. And the trick here is to factor out a 2 from every single term. We would have to pull a 2 out n times. So we have a 2n times 1 times 2 times 3 times 4 all the way up to n. That's n factorial. Thus, the denominator in this sum should be 2 to the n times n factorial. That second sum is similar and follows a similar trick. Here it's non-alternating, we don't have to worry about -1 to the n. We have even powers of x's, so if we're starting at n equals 0 for our sum, let's just make x to the 2n.
That'll take care of those powers of x's, but again, what about the denominator? If we write out the pattern in the denominator, it's 2 squared times 4 squared times 6 squared, all the way up to 2n squared. We can use the same idea as last time by factoring out a 2 to the n twice, or in other words, factoring out a 2 to the 2n. And then what are we left with inside the parentheses? 1 squared times 2 squared times 3 squared all the way up to n squared. That's actually n factorial all squared. Now we've rewritten our integrand using summation notation after finding those tricky patterns, but we're still not any closer to actually integrating this. Maybe we can use our knowledge of power series to rewrite one of these sums as a function we know and love. Take a look at that first series and think about the power series of e to the x. If we can rearrange this, let's just leave the n factorial in the denominator. Let's combine the negative 1 to the n over 2 to the n along with the x to the 2n, taking out that x to the first, and we can rewrite this in terms of a power series representation of e to the x. We can take that extra x out front, and what we have is e to the x, but it's not x on the inside, it's minus x squared over 2 on the inside. So really this first sum is a fancy way to write x times e to the minus x squared over 2. That second sum has an n factorial squared in the denominator. I don't know a great power series to take advantage of that, so we'll just leave it alone for now. Although you could try to rewrite that sum in terms of some cosine power series, or maybe even you could try integration by parts here, I think the most direct approach is to use a u substitution. That x times e to the minus x squared over 2 is just begging to use a substitution, so let's let u be x squared over 2. That'll make du x dx, and we can substitute that into the integrand. We'll just have e to the minus u. This works out very nicely because the x dx just cancels to make du, and if we look at those limits of integration from 0 to infinity, well, those are going to be the exact same limits of integration for du. When we substitute 0 for x in our substitution, we get 0 for u, and we can't necessarily plug in infinity, but if we let x go towards infinity, then u would also go towards infinity in our substitution. Now, thanks to that second infinite sum, we still have some x's lingering about. We'll have to change those to u if we want to integrate this. You might call this back substitution. Let's find out what x is in terms of u. In fact, here's a nice little trick. Since we have x to the 2n, let's just write that as x squared all to the n, because we can rewrite our substitution in terms of x squared. Just take our substitution, multiply both sides by 2, and we'll see that 2u is equal to x squared. Substitute that into this infinite sum. Maybe you'd like to take a second and cancel the 2 to the n in the numerator with one of the 2 to the n's in the denominator, and we're getting a little bit closer. Now, something that often happens with these types of problems, let's take that infinite sum and anything that doesn't have a u attached outside the definite integral. In terms of the definite integral, if there's no u, it's just a constant. Now our job is to integrate this, and if you've seen other videos on my channel, you know that this is one of my favorites. This is a different representation for the gamma function. Typically, gamma of n is represented as this definite integral we have here, just with an n minus 1 instead of a single n like we have here. So really, this definite integral equals gamma of n plus 1, which is well known to be n factorial. And we're finally able to deal with that pesky n factorial squared, since we can just cancel out an n factorial in the numerator and denominator. And you might think we're done. Indeed, this is a great answer, but we can do even better. Think back to how we originally rewrote that first infinite sum using the power series representation of e to the x. That's pretty similar to what we have here. Keep the n factorial in the denominator, bring the 2 to the n in the numerator. 1 to the n is simply 1. And this is exactly the power series representation of e to the x again. It's just we don't have x substituted in, we have 1/2 substituted in, and this sum exactly equals e to the 1/2, or the square root of e. I bet that's not the answer you were expecting looking at that first definite integral.
Let's solve this integral, the integral of f inverse of x. This is pretty interesting that we can even do this at all. Integrating any inverse function, we're going to find the result in terms of the inverse function and the antiderivative of the original function. This is a pretty cool trick, a pretty cool formula that you can use in a variety of situations. Now, the way we're going to do this, I don't think it's very intuitive. First, we'll do a substitution, and then we're going to do integration by parts. So let me show you that substitution. I'm going to let u, so it'll be a u substitution, I'm going to let u be f inverse of x. Or another way of saying this would be that f of u is simply x. If you think about how properties of inverses work, I sort of take both sides with an f. Well, okay, let's plug this into our integral now. This would be the integral of f inverse. Well, x I'm saying is f of u, so I'll stick in f of u here. And so now my integrand is in terms of u's. I probably don't want a dx here, so let's figure out what dx is by taking the differential of our substitution. We'll take that dx is, well, I need to take the derivative of the other side, or the differential of the other side. I'll simply just call it df of u. So that's what dx is, and we're replacing that right here. Now we have df of u. Well, we can do a little bit of simplification now, can't we? Since we have f inverse of f of u, we know that's simply u. That's how inverses work. When we compose inverses either way around, they just output the underlying variable. In this case, u. So now we have the integral of u df of u. And this is where we apply that integration by parts idea. We're going to let u be, well, typically in integration by parts, we would call this u. Maybe I'll simply call this u1 is u, and maybe again, I'm slightly abusing the notation here. I think when a lot of people do this proof, they use the letter z instead of u, but I'm going to let u1 be u. That would make du1 du, and I need the df of u. This will be our dv. This will be df of u. And to get v, we would antiderive. Well, what's the antiderivative of the differential? It's simply the function itself, f of u here. So now apply integration by parts. I like to do arrow this way minus arrow this way. That's how I remember it. So it will be u f of u minus the integral of f of u du. And finally, we actually have an integral we can compute, the antiderivative of f of u du. Well, I'll just use the notation capital F of u, where capital F represents the antiderivative of little f. This is the notation you might see in the fundamental theorem of calculus. As I say, every good indefinite integral deserves plus c. And we actually computed the integral here. It's in terms of the regular function f and its antiderivative capital F, but we started with x's. We should probably end with x's. So what was u? Well, look at the original. U was our original substitution, f inverse of x. So I'm just going to replace that here. U is f inverse of x. We have f of u, so f of f inverse of x. Lots of inverse stuff going on here. Minus capital F of u, f inverse of x again, plus c. And we can do one more simplifying trick. We have again here f composed with f inverse going the other way around. We know this to simply be x. So we'll write the final form. I'll just write x first because it looks a little nicer. X f inverse of x minus, and instead of writing this notation, this composition notation, sometimes you'll see the little circle, the composition symbol f circle f inverse of x, plus c, of course. Hey everyone, it's Brian. In this video, we're going to solve this integral, the integral of arctan x dx, or the integral of inverse tangent. This is a common type of integral you would see in a Calc 2 class, and it can be a little bit tricky since it doesn't look like it follows any of the regular integration techniques that you learn. And so when we're dealing with something like this, it's similar to how you integrate the natural log of x. We're sort of left to do integration by parts. That's what we'll do here. And for integration by parts, we need to select part of the integrand as u and the other part as dv, or v prime if you like. Well, there's not much of a choice here. Let's just select the entire arctangent to be our u, and that will make our dx our dv. So I'll write that here again for you. I'll let u be arctan x. And we know when we select u, we need the du. Taking the derivative here, you have to remember the derivative of arctangent x. That's 1 over 1 plus x squared. And since we're using differentials here, I really should put a dx here as well. And then depends on where you like to write this. I typically like to write the dv down here, but some people like to write it up here. This time we go the other way. The antiderivative of dx, well, that would be v. The antiderivative of 1 dx is just x. Now I write it this way because I like to remember how integration by parts works like this. It's u times v, so I do an arrow that way, minus the integral of v du. I do a little arrow that way. So it's u times v. That would be arctan x times x. I'll simply write this as x arctan x. Looks a little bit better. And then it's minus the integral of the arrow going the other way. That's x times 1 over 1 plus x squared. Or I'll just say x over 1 plus x squared dx. And now we have a new integral to solve. Fortunately, this one is much nicer. This one we can solve via a simple u substitution. Here we'll take u to be 1 plus x squared, since its derivative is just x up top off by a constant, we'll see. And maybe I shouldn't use the letter u. I already used the letter u, so maybe I'll just call this an s substitution. Use whatever letter you like. You could say u1 if you want. S will be 1 plus x squared. That makes ds 2x dx. And we're seeing that, well, this is just twice the numerator. We can make this substitution. This integral, and you'll forgive me, I'm running out of space here, will be minus 1/2 when we divide both sides by 2 here. If you like, you could say that dx is ds over 2x, and that's where that 1/2 is coming out front. We'd have the integral. The x dx, that's becoming our ds, and this is over what I'm calling s. Now you just have to remember, what's the antiderivative of ds over s? Well, that's going to be with a 1/2 out front, natural log absolute value of s. I should say plus c, plus a constant here. So now we're ready to write the full answer. I still have this x arctan of x out front here, x arctan of x, but then it was minus this integral here. I went a little bit all over the place, but I hope you'll forgive me. It's not natural log of s. We're not really interested in s here. We want our final answer to be in x's. We started with x's, we should end with x's. So what should s be? Well, we had s being 1 plus x squared here. In absolute value, every good indefinite integral deserves plus c, as I say. Hey everyone, it's Brian. In this video, we're going to solve this problem, the integral, the antiderivative of the absolute value of x dx. And this is a little bit tricky because if you know anything about the absolute value function, it's not differentiable at 0. It has that pointy edge, that cusp, if you will, that makes it not differentiable at 0. But we can actually antiderive it just fine. And we'll do it by writing the absolute value in terms of its piecewise definition. The absolute value of x, what is it really? Well, it's simply x if x is greater than or equal to 0, and it's minus x if x is less than 0. That gives it its V shape, where it's a positively sloped line after 0, a negatively sloped line before 0, and what makes any input output to be a positive value. You think the absolute value of 5 is 5, the absolute value of negative 5 is 5. So how do we actually integrate this? Well, we'll just integrate the pieces. So if I want to antiderive this, it's exactly the same. And I don't know if this is very good notation or not, but I'm just going to kind of put this in piecewise notation here and just sort of integrate the individual pieces. Again, I'm probably abusing some notation here, but I think we'll be okay. We'll get the idea down. And all we have to do is antiderive each individual piece on its respective domain. And so what's the antiderivative of x dx? Well, it's x squared over 2 plus c, of course. We're doing antiderivatives, and this is for x greater than or equal to 0. And same deal for minus x. Add 1 to the power, divide by the new power. I need plus c. Again, maybe I'm slightly abusing the notation here using 2 c's, but I think we're okay. You'll get the idea. And that's if x is less than 0. And hey, there we go. We found the antiderivative of the absolute value of x. We just had to split it up using its piecewise definition. Now, I would encourage you to click the video on the screen so you can watch the next video. I'll see you in that one.